Hello, everyone, and welcome to week 23 of Qubit by Qubit. As you can tell from the slide here, today's lab is going to be tying it all together. In other words, doing sort of a full-on review of all the things that we've learned in this course, how they all relate to each other, how they all relate to quantum computing on sort of a higher level, and hopefully just giving you a good solid review of what we've learned. Now, even though that sounds a lot like this is the last lab, it is not. I will repeat this again in a little bit. We still have a lab next week where we'll be talking about sort of looking ahead, some near-term future work in quantum computing, some of the most promising algorithms for the short term. But for various logistical reasons, we have chosen to put this review lecture as the second last lab in the course. Now, before we get into it, this is kind of like a celebration as well. I know that many of you have expressed a little bit of sadness, if you can call it that, that we are coming to the end of this course. It has certainly been a fun journey for me, and I hope it has been a fun journey for you as well. I think now, as the review lecture, is as good of a time as any to sort of take a step back and consider just how much you have learned in the past, well, 8 months or so, right? Or even 7 months. We started in October. We've gone through a whole bunch of mathematical basics, right? From linear algebra to complex numbers and probability. We learned to program in Python. We learned about Qiskit, not to mention all of the fundamentals of quantum computing around what qubits are, and all of the kind of weird and sometimes counterintuitive intuitions with those, from superposition, interference, entanglement. All of these things are things that you are now familiar with enough to talk about algorithms like Grover search or superdense coding or quantum teleportation. And hopefully you also understand that quantum teleportation is not actually teleporting real world objects. So there's been a ton in the past 8 months. Of course, I am not going to be covering everything in a ton of detail in this 1 hour lab. It is going to be a pretty quick high level review, but hopefully it just serves as a way to, again, tie it all together, cinch it up, and contextualize everything that we've taught so far. Okay, the program for today, we have actually quite a few announcements just as we're coming up on the end of the course. There are some logistical items to cover. Then we'll do our Canvas attendance quiz and pre-lab Zoom feedback as always. The lab content is going to be entirely on the slides, entirely with me talking through the various concepts we've learned. I think we have like one review problem, or maybe two, but mostly it'll just be a review of content followed by post-lab Zoom feedback. We don't have any optional content today, so I'm hoping to get through all of this within the next hour. But then, as always, I will stick around afterward to answer any miscellaneous questions. Okay, so let's do the first of the announcements. This one is about the homework for this week. Instead of doing a regular homework assignment, we have two sort of special assignments. The first is the technical assessment, and then the second is the post-course survey. So let's talk about the technical assessment first. This one, the main thing I want to point out is that the due date and timelines are a little bit different than what we normally have for assignments. So the technical assessment will be available to submit for 3 days following your lab section. So especially for us, because we are on a Tuesday, this is different than the normal weekend deadline. So make sure that you get this assessment done within the next 3 days, starting from the end of this lab today. You will have 50 minutes, 50, to complete the assessment. So pick a time in the next 3 days where you have at least an hour to sit down and do the assessment, and then try and write it entirely in one 50-minute block. Please complete the assessment to the best of your ability. The reason that we're doing this, number one, I hope that it's a good review for you to sort of go back and exercise your brain a little bit in some of those earlier concepts in the course. It's also going to be helpful for us, though, so that we know just how far you've come as well. We can quantify it a little bit and actually learn where we could do a better job of teaching, perhaps. That being said, just to be very clear about this, the technical assessment, as far as grades are concerned, is just based on completion. So if you submit the assessment, you will receive full credit regardless of your score. We do ask that you do your best on this, though, just so we have a fairly accurate understanding of where your, well, where your level of understanding is. Okay, and then the post-course survey, number 2 here, you will be receiving a link to this in an email. This one is not technical. This is a bunch of sort of, well, it's a survey. We're asking for feedback on how we've run the course and all that kind of thing. This is required in order to receive the certificate for this course. The deadline for this is May 5th. So not as much rush on this one. Yeah, I mean, obviously it's required for the certificate. I would also just ask you to do this to help us out. I think one aspect of this course that was not even entirely clear to me when I first started, but certainly has become clear now, is that this is really a pretty significant and well, on the edge of what we know experiment, because bringing quantum computing to high schoolers has been done in sort of small ways before. This is another fairly large experiment in that area, though. And so there's lots of people who will want to know how this course went, what things we liked, what things we didn't. And of course, I can answer those questions all I like, but you as the students are the ones who really know the true answers. And that's why we want to get a lot of this feedback from you now. So one last announcement then is sort of a continuation of this course, if you will. Not a formal course, I guess, but this is a little fun thing. So if you still have questions about quantum computing, if you'd still like to stay connected and you still want to hear members of our team, myself, the other TAs, Fran and Amir, talk about their favorite topics in quantum, we are starting up a live stream called Schrodinger's Chat, which I think is a absolutely brilliant name for this. Basically, we will be hopping onto this on some schedule, not exactly sure when. Akshay, our head TA, will be running it and sort of moderating and running these discussions. And we'll just have cool people on to talk about all kinds of stuff in quantum computing. So there will be more information on this coming out very soon, but it will be hosted on Twitch. So we already set up a Qubit by Qubit Twitch account at twitch.tv/Qubit by Qubit. That's where we'll be hosting it. Many more details to come, though, over the summer as we sort of finalize who we're going to have on and exactly how we're going to run this. Just to be totally clear, this is 100% optional. It happens during the summer. The course is going to be over. But we've heard from a lot of you that you enjoy hearing us talk about various topics in quantum computing. And so this is going to be sort of an informal continuation on that subject. Okay, that's all of our announcements done. I know I said there were several of them, but we've gotten through them all. Let's go over to the attendance quiz now. We are lab number 1. The quiz password is 4050. And today's question is, which potential applications of quantum computing are you most excited about? So open-ended, of course, there is no correct answer to this. It's just whatever you think is interesting. I will open up the chat as well in case anybody has questions about the Canvas attendance quiz or any of the announcements. Feel free to throw those in the chat. And last but not least, we have our pre-lab Zoom feedback, and then I promise we will get into the actual lab itself. Okay, so no questions on the announcements, or here we go. The homework grades would be added to our previous scores or not. Assuming you're referring to the technical assessment, my understanding, although if you're really concerned about this, I would suggest posting just to confirm, like posting on Piazza. My understanding, though, is that the completion grade, so just doing the technical assessment, filling it out, will count as a 100% grade for one homework. That's my understanding. Will we be provided an official score transcript? That's a good question. I don't know. The only thing I'm aware of is this sort of completion certificate. I don't know if they will be sort of sending out the scores and that kind of thing. So I would post to ask about that. Love the name Schrodinger's Chat. Yes, me too. I forget whose idea that was, but it is pretty awesome. Okay, somebody DMs me. Can we get entire course videos and materials even after course completion on Canvas or in any other platform? So I know I've seen a couple of questions on Piazza about this. I'm not aware if course administration has made a decision on whether we will keep all the videos and materials and things up. For the time being, at least for the course materials, and for those of you who have not gone to university yet, this is a great strategy for university as well. You can download all of the materials for yourself and save them somewhere, just in case you get access revoked at a later date. That being said, for the videos, storing all of these videos would probably not be very practical. I'm not sure if we will be keeping them up. So I would ask again on Piazza. Why not stream on YouTube? I'm not sure. We chose Twitch for some reason. Okay, cool. So somebody says in the chat that course administration has confirmed they won't be deleting the videos. So as long as you keep the YouTube links, because all these videos I think are unlisted. And so you need the actual link to be able to view it. But if you keep a hold of those links, then hopefully the videos should be up. People are asking if they're sure. I'm not endorsing that this is true. I'm just, yeah, if you want to confirm, perhaps check on Piazza or just ask a question yourself. And I'm sure someone will be able to follow up. Okay, yeah, sorry I don't have better answers for you on this one. Like I said, I'm not even sure if a final decision has been made. So yeah, actually, I'll write a note to self. I can follow up on some of these as well, and I'll include them in my communication to you later today. Okay, awesome. So I'm going to pause on those questions related to keeping materials and that sort of stuff. And let's move on to the lab. I will say today's lab is kind of long, or at least it has a lot of slides. We'll see how fast we can go through them. But yeah, there's a lot of stuff to review. Okay, I will also go ahead and share the results of the pre-lab Zoom poll. So this week, by the way, as it said on the previous slide here, Amir talked about some physical implementations of quantum technologies. Unfortunately, I won't be reviewing those topics. As I said, today is a review. But again, the homework this week has nothing to do with physical implementations. It is just this technical assessment, which will be a review. Okay, agenda for today, we are revisiting a whole bunch of core quantum concepts. You can read them off here: qubits, operations, circuits, algorithms, and applications. And I will sort of talk about this structure, and then we'll walk through each of these in turn. And then another reminder here for anybody who was not in the lab at the very beginning when I said this: even though today is the big review and sort of summary lecture, it is not the last lab. We still have one more week, and that's going to be next week. And in that, we will be talking about near-term algorithms, which is basically just, the algorithms we've talked about so far are really interesting and powerful, but probably not going to be run on any real quantum computers anytime soon. So next week, we're going to talk about some of the algorithms that are being run on today's quantum computers, literally as we speak, and then some of the outlook in the next 2 to 5 years. Okay, so let's start off at the very highest level we possibly can. We spent 8 months in this course. How would you define quantum computing? So you can throw an answer in the chat if you want, but just at least think about this for yourself. How would you define quantum computing, given all that you know now? I'll give just a few seconds here for you to think about that. So the computing part of this is pretty straightforward because we are sort of trying to solve problems. We're trying to use algorithms. Obviously, there's been a lot of computer science and programming in what we've been doing. The quantum part, though, is the part that we really want to focus on. It's the use of properties of quantum mechanics to solve certain problems more efficiently than classical computers. So a few notes here. The properties of quantum mechanics we will be reviewing in a moment, but these are certain physics rules that we straight up did not know, or at least didn't have experimental evidence for at the time when classical computers were created. And so when we ask the question, how do we solve some of the most computationally difficult problems we know, we go to nature and we say, what does nature allow us to do? quantum mechanics is the most fundamental definition of what nature allows us to do. And that's why we build our model of computation on top of quantum mechanics. The other thing I want to underline here is that quantum computing allows you to solve certain problems more efficiently than classical computers. One of the big misconceptions in a lot of popular science is that quantum computing is going to like revolutionize everything. You're going to have some kind of super quantum computers in your phones in 2 decades, and it's going to make them run way faster. No, probably not, right? As you've learned here, the algorithms where quantum computers are useful are fairly specific, right? Something like Grover's search solves a very specific problem, and that's where quantum computers could be useful. It's to solve these certain problems faster than any classical computer could. Okay, so let's do a quick overview of what we have learned. I actually think this is a really useful way to conceptualize and think about all the different things we've learned in this course. We've sort of been building from the core of quantum computing, which is the notion of qubits. If you think back to some of the very first topics we discussed was, what is a qubit? Well, it's represented by a 2-element vector. Both of those elements can be complex. We talked about a number of properties of qubits. From there, we built on that to talk about operations. So we learned that you can apply gates to qubits, and that would transform their state, and you can also measure them. And we had a whole discussion about measurement and how measurement in quantum is very different than, for example, measuring the length of your desk. It actually changes the state as well, and it has certain interesting properties. From there, then we progressed even further up to full circuits. And so we started looking at circuits that did certain things for us. We looked at circuits that created superpositions, circuits that created entanglement, all that kind of thing. And this was done by chaining together gates and measurements. After that, we looked at full algorithms and protocols. So this is things like Grover's search, superdense coding, etc. And these are circuits that do something interesting, I guess, for lack of a better word. We string together a certain series of gates and measurements. Maybe there's some classical stuff in there too, right? In quantum teleportation, for example, we had to send classical information. So there's a number of things that get added in algorithms and protocols to do certain interesting tasks. And then finally, the last layer that we've talked about is applications. And well, I guess to be honest, we haven't talked about these in a ton of detail. But the basic idea here is that every algorithm we know sort of relates to some real world application. So for example, Grover's search here is related to a number of real world applications. It can be used for database search, can also be used for optimization, and so on and so on. And at the end of the day, right, this is sort of the interface with the real world. Right? Because if you are a banker, or if you are an engineer, or if you are a mathematician or a physicist, what you care about ultimately is these applications. These are the things that quantum computers are going to do for you. And these applications are built on all of these underlying layers of concepts that we've covered in this course. And so the format for this review is going to be chronological to the course. I'll be going through things sort of from the beginning to the end. And that also corresponds to doing this diagram from the inside all the way to the outside. So naturally, we are going to start with qubits. So a qubit, this is a word that is short for quantum bit. And we learned a lot about bits in classical computing. They are sort of the fundamental unit of computing, where everything in your computer or your phone or your toaster or whatever is probably represented using zeros and ones. And we talked a bit about why that is. In quantum computers, we have the same idea of a fundamental unit of information, but now it is a qubit. Unlike a classical bit, which can be either 0 or 1, a qubit can represent a superposition of these states, right? So we can have things that are 50-50 ket 0 and ket 1. This is the most common sort of difference that people cite between regular bits and quantum bits. But there's another one too. Quantum bits or qubits can be in superpositions, and they can also have phases, right? And this is one of the reasons we used complex numbers. These states 1 over root 2 ket 0 plus ket 1 is different from 1 over 2 ket 0 minus ket 1, even though they represent the same superposition, right? Both of these represent a 50-50 0-1 state. But they are different states because they have different phases. And remember, the phase is just that sign in front of the ket1 here. So qubits are really different than classical bits in quite a number of ways. Now, how do we actually do that? Well, this is something that we actually just recently talked about, right? We talked about it last week in week 22. The question comes, okay, we have this nice mathematical model of what a qubit is. It's a two-dimensional vector of complex numbers. What is that actually? Like in real life, what is that qubit object that we're describing? And we saw last week that there are many of them, and I've mentioned these in previous labs as well. These are just a small selection of the possible qubits out there. There's actually many of them because anything that is sufficiently small follows the rules of quantum mechanics, whether that's a photon, an ion, an electron, and so on and so on. And so anything that obeys the rules of quantum mechanics, with a couple other considerations, but mostly anything that obeys the rules of quantum mechanics at this very small scale can be used as a qubit. One of these constraints that I referred to, where something has to follow quantum mechanics, the second important one is that it has to create a two-level system. So there basically have to be two different physical states to represent our zeros and ones. For example, in trapped ion, we learned that this was the energy level of the electron, right? I think I talked about this a few times, where ket 0 is where the electron is in a low energy orbital. And then if you pump the electron up to a higher energy orbital, that would be ket 1. So those are two levels in your system. In superconducting computers, for example, this fundamental two-level system is the direction of current, right? So if you imagine a loop of wire with electrons flowing through it, the electrons can either be flowing clockwise or they can be flowing counterclockwise. And that gives you the two levels required for a superconducting qubit. Now, all of these qubits have issues. They have physical imperfections. One of those that you'll hear talked about a lot is decoherence. And decoherence, very generally, is the loss of information stored in the qubits. So that can mean that you go from ket 0 to a random mush of superpositions. It can mean that your phases change over time. All that kind of stuff is some form of decoherence. Okay, so going back to the more mathematical definition of qubits, we talked about the difference between scalars and vectors. Scalars are just numbers. Vectors have a magnitude and a direction. And we use vectors to represent qubits. Also, each of these numbers can be complex, right? So we could have a qubit like, I don't know, ket psi equals I0, something like this, totally allowed. And the reason we have that is to account for phase, right? And again, phase is this idea that complex numbers, remember, complex numbers are represented in the complex plane. Two different complex numbers, even if they have the same magnitude, so for example, both of these, say, are on the unit circle, they can have different phases, right? And that just means that the angle between them is going to be different. So in order to try and capture all of that, because qubits with their two-dimensional complex nature can be very hard to visualize, we use something called the block sphere. So every qubit state can be represented as a vector on the surface of the block sphere, and vice versa. Every point on the surface of the block sphere represents a particular qubit state. So this is a really handy visualization. When we talked about the block sphere, I gave the rough intuition that the latitude, right? So which circular line you're on here, or which horizontal line you're on, the latitude represents the superposition in some sense, right? Their latitude tells you what chance you're going to measure 0 and what chance you're going to measure 1. So if you're on the equator, you're 50-50. If you're somewhere up here, you have a higher chance of measuring 0 than measuring 1. But we have two dimensions here, right? We have both our angle theta and our angle phi. And so which longitude you fall on, which is these lines here are the longitude lines, those tell you the phase, right? And so again, there's this dual concept of the probability of being in 0 or 1, and you also have some phase information. And the block sphere captures both of those things through theta and phi. I am sort of watching the chat. Feel free to keep your conversation going there about course materials. But if you do have any questions as I'm going through this review, I will try and take pauses to address questions. But feel free to just throw a question in the chat, and I will check them periodically. Okay, so I'm done the section on qubits, right? We reviewed how qubits are represented mathematically, physically, block sphere vectors, all that kind of stuff. I want to pause here before we go on to operations to ask if anybody has questions on qubits. Okay, so one person says, what is the physical meaning, I guess, of phases of qubit states? That's a good question. Let me see if I can answer that. I think, okay, so the first thing I would say, as with a lot of questions that have to do with physical implementations, it depends what physical implementation you're looking at. One that I think has the easiest interpretation is photonic qubits. So a photon, right, is a little packet of light. And light, if you've taken a physics course, is also known as electromagnetic radiation, right? And so light is literally an electric field and a magnetic field traveling at the same time. So for example, if I had a light over here, right, I could send photons in this direction. And what the photon actually looks like, although this is going to be very hard for me to draw, is, for example, say an electric field that goes like this. So you have a wave that represents the electric field. And then, let me maybe change colors here. So that one is going up and down. You also have a magnetic field that's going side to side. So if this one is in the sort of vertical direction, imagine that we also have a wave here going in the kind of horizontal direction, even though that's super hard for me to draw. Right? So this one is in the, X coordinate there, while our black wave here is in the Y coordinate direction. And then our wave is actually traveling in the Z direction, right? For example. So hopefully you can try and wrap your head around how this looks. So this is what a photon looks like. And this is, the qubits that are used inside a photonic computer. So your question is, what is phase? Well, let me first say what proportion is, right? So what the superposition between 0 and 1 is. That is the orientation of this wave here. So if your y is pointed straight up, that might be ket 0. But if you rotated this whole thing by 90 degrees so that your black wave was traveling horizontally and your blue wave was traveling vertically, then you would have ket 1. And you can have superpositions by rotating an angle of 45 degrees, for example, to be in a 50-50 superposition. What phase means in this context is whether the electric and magnetic fields are aligned with each other. What I mean by that is, the way I've drawn it here, both of them go out, right? So the electric field goes up, the magnetic field goes to the side, and then they both come back and meet at the same point. That does not have to be the case. It could be that the whole magnetic wave is shifted up a little bit so that it never actually meets the electric wave here, right? It could be that our magnetic wave kind of goes like this, right? This is really hard to draw, but basically, if your magnetic and electric waves are not perfectly in sync, that is phase. So it's kind of just, it's two properties of what makes up a photon, which can definitely be difficult to visualize. I totally get that. I don't know if there's a good intuition for phase in other types of qubits. It's certainly a counterintuitive and weird property. Okay, so somebody asks, please tell the difference between superposition and entanglement and what is their physical interpretation? Right, so I'll do this one more question and then I will move on just for the sake of time. Superposition is quite simply any state that has a sum in it, right? So ket0 plus ket1, that's a superposition. Ket0, that's not a superposition, right? So superposition is just a fancy word that means you have a chance of measuring this state or you have a chance of getting more than one measurement result as a result of measuring that state, right? So in this case, I have a 50-50 chance of measuring 0 or 1. Here, I'm always going to get 0. And so 1 is a superposition, 1 is not. Entanglement, on the other hand, is a more involved definition, which I won't go over here, but it has to do with conditional probability, right? Where if you measure the first qubit, does that change the probabilities of measuring the second qubit? But entanglement is a property of 2 or more qubits, right? So for example, a state that looks like this is an entangled state. Now, the conditional probability definition can be a little bit difficult. So another way to think about entangled states is, can you write them as individual qubits? So let me give you an example. Suppose I have this state up here, and then I also have this state down here. And I ask you which of these is entangled, right? Let's try to write these as individual qubits, right? If you notice this second one, I could write this as ket0 plus ket1 all times ket1, because the second qubit is always ket1 here, right? So we can use like the distributive property, basically, to sort of factor out that common ket1. Because we're able to write this as only single qubit states, notice that all of our kets here only have a single qubit, this is not entangled. If you can sort of pull apart your state and write it as single qubit states only, then it's not entangled. I challenge you to try and do the same thing with this state. You'll notice there's no common factors that you can sort of pull out of this expression. Therefore, this state is entangled. So hopefully that is helpful. Physical interpretation, I think I'm not going to go into that right now, just for the sake of time. Superposition, I already described, right? That was sort of, you can picture it, at least for a photonic qubit, as being a certain rotation of those waves. But for other qubits, it gets kind of messy, right? Because, for example, with an electron being in one orbital or another, it's kind of like being in two places at the same time, where it's partly in the lower orbital and it's partly in the upper orbital. I don't really know if that has a nice, clean intuition behind it. Okay, great questions. If you still have more questions, please feel free to post them on Piazza. I'm just going to keep going for the sake of time. Let's talk a little bit about quantum operations. So in quantum computing, we have these things called qubits, and obviously we want to be able to change them in some way. That's how we're going to do our computation. Manipulating qubits is done with gates, right? So at the fundamental level, all a gate is some, well, it's a mathematical representation of some physical process that changes the qubit. So for example, shining a laser on an atom is going to change what state it's in. And so we call that laser a gate. So gates allow us to use 3 of these major quantum resources: superposition, interference, and entanglement. We cannot get any of these things without using gates. And then the other operation we talked about was measurement. And remember, measurement is not just another gate. It is sort of fundamentally different. It collapses our quantum state. It destroys any superposition. And in that way, it actually does change our quantum state. So the physical implementation of gates, I already alluded to this a little bit. As with any physical implementation question, it depends on what types of qubits you're using. But as one example here, in a trapped ion system, a laser beam shone on the ion is a gate, right? And what that laser beam is going to do is it's going to jump our electron from some lower orbital. So you can imagine this is sort of a small orbital up to some larger orbital up here, E2. Right? And our laser is going to have some particular energy that is equivalent to the gap between the energy in that lower state and the energy in that higher state. This is very much a physics thing, so don't worry too much about it. But suffice it to say that gates are processes that change qubits. So how do we do this in math then, right? So the physical implementation we actually only really talked about last week. We've been talking about the mathematical representation for quite a while, though. Remember, qubits are vectors, so I've just kind of drawn them on a 2D plane here. I know that these can't be complex, so it's not a perfect representation, but let's roll with it for now. Suppose you have one qubit in the state U1, and then you have another qubit in the state U2. We want to change the qubit state from state U1 to state U2. This is a transformation, right? It's a movement of our state, and that transformation is done by a matrix. So remember when we learned about matrices, I basically said that the matrix is to linear algebra what a function is to all the math you have learned so far, right? A matrix is basically just a fancy way of writing a function. Not quite, I went into more detail, but that's the idea. It takes an input and it spits out an output. So in the world of quantum computing, then, we have our qubits, which are represented by vectors, and we have our gates, which are represented by matrices. So whenever you get some expression that looks like a matrix, you automatically know it's a gate. And if you ever see something that looks like a vector, you automatically know it's a state. Okay, so to actually learn how these gates manipulate states, we had to learn linear algebra, which is actually kind of a big topic, but we did it way back at the beginning of the course. And we tied that into quantum circuits. So for example, we learned what this diagram means. This diagram means that we start with an initial state 0, 1. And as a reminder, that is equal to ket1. Then we apply an H gate. Then we apply an X gate. And we could totally ask you a question where we say, what state do you end up in? Now, the recommended way of doing this would be to use matrix vector multiplication, right? And remember, for that, you look at the row of the matrix with the column of your vector. You do sort of multiplication, you sum them together. There's a whole process there, which I won't review right now. But yeah, then you just have to solve this whole equation. You carry out the computations, and you get this as your final state. Now, one significant reminder here, just to really drive this point home, when you write things in linear algebra notation, because of the order of multiplication, you have to reverse the order of your gates, right? So notice here, even though we have hx in the circuit, we've written xh in the multiplication. That does make a difference. Order does matter here. So just be careful of this. This is something that trips up even people who are in the industry all the time. But the intuition for this is that we are first applying the H gate. So we start from our vector and we first apply or multiply with the H gate. Once we've done that, then we are going to multiply with the X gate. And because we always write multiplication with the matrix on the left and the vector on the right, we end up getting this swapping business going on, right? The earliest gate in the circuit comes on the right, and the later gates in the circuit come on the left. Okay, so let's, I've been talking for a while. Let's have you all work through a particular question. This one is a review from pretty early on in the course. What are the possible results of measuring this state, ket psi equals 3/5 0 plus 4/5 1? And then what are the probabilities of each of those results? So there's two questions here in the Zoom poll. Both of them only have a single correct answer. So go ahead, try and work out what you think the answer is to this problem. Once 50% of you have answered, then I will go over it and review. Oh, interesting. Someone says they're getting a blank poll. I do see people responding to the poll. So it might be Something on your side? Or I might have set it up wrong. I'm not sure. Okay. Yeah, I'm not sure. I will go over the answers here, though. I mean, in theory, you should be able to do this problem anyway. It doesn't matter if it's multiple choice, right? But yeah. Okay, so we have about 50% of you who have answered. So I will go ahead and start walking through my solution. First question is, what are the possible results of measuring this state? So this is a bit of a tricky question. Well, okay, so this is some kind of superposition between 0 and 1, right? Now, remember back to when we learned the postulates of quantum mechanics, we had our states being represented by these kets here, these vectors 0 and 1. But then when we measure a particular quantum state, we always get eigenvalues as the result, right? Which I guess I should have been a little bit more accurate in this particular poll. I never gave you +1 and -1 as the answers. So I'll be a little bit lenient on this. Usually, though, we would say that the results of measurement here are scalar values 0 or 1. And the reason for that is just that, when you measure this result, you're going to get some, value on a voltmeter, or you're going to get some measurement on an instrument in the lab. That is a scalar value. It's not actually a vector, right? You're never going to get a superposition, for example, as the result of the measurement. So I know a lot of you put ket 0 and ket 1 as the two possible results. That's totally the right idea. But I would say probably the more correct answer here is to say the scalar values 0 or 1. And by the way, this is oftentimes a convention used in quantum computing, where your basis vectors are written as kets, right? Just as we have here. And then the measurement results are written inside the ket, right? So here the measurement results are 0 and 1. Those are written inside the ket. Sometimes you'll also see stuff written like this, though, right? You might see ket up and ket down. What does that mean? It means that if you measured this state, you would get down, or sorry, up, whatever that means. And if you measured this state, you would get down, whatever that means. Oh, some people are pointing out that they didn't say or. Yeah, you're right. It should really be 0 or 1. Certainly not a superposition. Good catch. Okay, so let's go on to the second question then. The second one is, what are the probabilities of each of these results? So here, remember that the postulate or the procedure for probabilities is to square the amplitudes, right? So here we take our coefficients and we square them. So the first one is going to be 3/5 squared, which is 9/25. And the second one is going to be 4/5 squared, which is 16/25. Now, there is a minor mistake that I have made here, kind of on purpose, just to remind you. This is correct because all of our amplitudes are real. But if you had complex numbers anywhere up here, you need to remember to take the modulus. And a good sort of check that you can always do, after you do this procedure where you square all of the coefficients, they should sum to 1. If they don't sum to 1, chances are you have forgotten this modulus step. That's a really common error. Okay. So quick review. I know that was from quite a while ago, so hopefully that refreshes some of your knowledge. Now, to sort of end off this section on operations and qubits as a bit of a summary, all of these things in these first two layers here are sort of what we generally refer to as quantum mechanics. So this is kind of more on the physics side than the computer science side. And you'll notice that as we start going up to circuits, algorithms, and applications, that is where we start getting into quantum computing more so, right? So quantum mechanics, the rules of quantum mechanics, the postulates, they tell us how we represent operations, how we represent states, how we do probabilities, how we do measurement. Remember, we had a whole lecture on the postulates of quantum mechanics. And that's basically all the rules for how qubits and operations behave. One example that we had from that part of the course was the Stern-Gerlach and double slit experiments, which demonstrated some of these properties that we've referred to in the past couple slides. Okay, so then, I mean, a natural question here is why all the math, right? We have this distinction between what happens in the physical world, what happens in real life, and what happens in the math world. And the answer for this is basically that people tried experiments and they observed that qubits display superposition, interference, and entanglement. So one term that I don't think we ever officially introduced, but it's a great descriptor for this. Quantum mechanics is what we call phenomenological, which is a I can't even spell it, phenomenological, which basically means that it is based on observation. There was no Einstein who sat down and came up with a really smart theory of quantum mechanics. It was a whole bunch of experiments that built up a picture of what the physical world is. And then mathematicians came in afterward to try and build math that made all those observations true, right? So usually in physics, you think about it going from theory, someone has a really smart theory and then it's proved in experiment. That's not what happened in quantum computing. Quantum computing went from experiment to theory. And so that's why we have all of this kind of math that doesn't necessarily have a nice justification, right? Like Einstein's theory of relativity, if you ever have a chance to learn about that, it's a very elegant, nice theory because it started from the math, right? It started from a better understanding of how the math should work and was then proven in experiments. Here, we've kind of been like piecing things together until we had some model that makes our experiments true. So a few properties of that math, right? This is what I pretty much just said. This math is our attempt at describing what we observe happens in qubits. We use vectors for qubits because they can't easily be described by just a single number, right? We kind of need both of these numbers to describe both superposition and phase, right? This is one question that actually I often get at the very beginning of courses like this, is couldn't you just use a single number to represent a superposition, right? If you had a 50-50 superposition, why can't you just call that 0.5? The answer is phases, right? If you just used a single number to represent superpositions like this, you cannot have phases. Okay, so here we go. Why use complex numbers for qubits? Again, it's because phases and therefore interference cannot be easily described by real numbers. And then why do we use matrices? Well, just because matrices are the most natural way to operate on vectors. Okay, so to wrap up this section, the three main quantum resources that contribute to speed ups and to the increased performance that everyone knows and loves in quantum computing are the following. Superposition, right? So superposition refers to the fact that n qubits can be in any combination of 2 to the n classical states, right? And this just means, again, here we have an example of a superposition. You can be in many states, quote unquote, at the same time. The implication is that quantum computers often use fewer resources than classical computers to represent a lot of information. So even though today's quantum computers are only 60 or 70 qubits, and you probably know that a computer has like 2 or 4 or 8 or 16 gigabytes of RAM, like billions of bits, right? Even though there's a huge difference between those two numbers, even quantum computers that have 60 or 70 qubits can still do interesting computations. Okay, second one is interference. Interference refers to the fact that some of the classical states in a superposition can cancel out, right? So we saw some examples of this in previous algorithms, and the implication of interference is that quantum computers can often converge to the correct solution by canceling out the wrong choices and amplifying or constructively interfering the right one. The best example of this is Grover's search, where we saw the correct solution sort of being amplified bigger and bigger. and the wrong ones got closer and closer to 0. And then the final one here, which is another one that everybody's heard of in popular science literature, is entanglement. So here is a classic example of an entangled state. Some multi-qubit states cannot be represented classically, right? And this is pretty much what I said on the earlier slide, where you cannot write this as some combination of single qubit states, right? There are no alpha, beta, gamma, delta that make this true. And so the implication here is that quantum computers can often access and utilize states that are traditionally inaccessible to a computer. So all the algorithms we've learned that have speedups over classical computers use one or all or a combination of all of these different factors to get that speedup. Okay, so let's move on to the next layer up, which is quantum circuits. Hopefully this is fairly straightforward because it really does build on the linear algebra. So the idea with this layer is that we combine states, gates, and measurements to create a cohesive thing called a quantum circuit. And the main thing that we taught in this course was how you use Qiskit to create and run these circuits. Okay, so a couple of examples of quantum circuits here. You can put all qubits in a superposition by using Hadamard gates. You can create an entangled state or do a Bell measurement by using something like this. And you can get really complicated states or really complicated circuits like this, right? Which was the 2-qubit Grover diffusion circuit. And if you don't remember what the diffusion circuit is, feel free to go back and review that, but it's kind of a technical detail. So all of these are quantum circuits, all of them, well, I guess not this one, but the other two have been drawn using Qiskit. And so when we learned about Qiskit, we saw that there are several steps that you would usually take, right? The first step is that you create the circuit. So you tell the computer either through code or through the composer which gates you want to apply to which qubits when. Step 2 is usually then to simulate the circuit. And we did a lot of this. We asked the computer to go ahead and simulate the circuit using the rules it knows about quantum mechanics. So there's no actual quantum computers being run here. It's just using all these laws of vectors and matrices to tell you what the correct answer should be. Step 3 is then to run on actual hardware. So this one we often skipped just because it takes longer. Today's quantum computers are not super fast and very expensive to run. And so we often don't do this just because, you know, we can do a lot of the algorithms we've learned on a simulator. But usually what you do is run your simulation with some small number of qubits. Maybe you run it with like 10 qubits, just to make sure it works as you expect. And then you step up to a real quantum computer to run your 50 qubit computation, which you actually don't know the answer to, right? So this step 2 is kind of like verify my circuit is correct. Step 3 is then solve the actual problem. And then a last sort of catch-all step here is to evaluate the outcome and try to quantify your errors. So that's actually all I had on circuits. I see one question in the chat, so let me just address that real quick. In physics, interference is the superposition of two waves of the same frequency with 0 or 180 degrees of phase difference. So if superposition and interference, are they also related in quantum computing? Yes, absolutely. And I would say the visualization that you named there, where you have waves that are sort of in or out of phase, is that's a perfect way to think about it in quantum computing as well. You can have things that are exactly 0 or 180, so exactly constructively or destructively interfering, but you can also have things that are like 37 degrees out of phase, and then you get some different superposition. So 100%, it's the same idea. That's why, by the way, we learned a little bit about waves when we talked about wave-particle duality, because a lot of these concepts with like superposition and interference, they come from the study of waves. And so that's a perfect visualization. Okay, sorry. So I was going to talk about algorithms and protocols going up in our stack here. So Oh, excuse me. A quantum algorithm is then just a set of steps that uses these circuits to provide a speed advantage for certain types of problems. Again, certain types is highlighted here because quantum computers are categorically not just universally faster than a classical computer. To carry out an algorithm, we often talked about the steps first in English, and then we translated that to a circuit, coding it using Qiskit. So I've just picked Grover's algorithm here as sort of an arbitrary example of one possible algorithm, or sorry, yeah, one possible algorithm that we've learned. So first we would describe it in English, right? We're going to create a superposition by applying H-gate to all qubits. Then we're going to apply the oracle and the diffusion operator, which induces interference. And then finally, we're going to measure all the qubits. That's kind of like step one of our algorithm. Then we went and typed in a bunch of stuff into our notebook, and we got a particular circuit for this. And then once we've specified the circuit, we can go ahead and run it using simulations and hardware, right? And that's basically how you run an algorithm. Now, the distinction between a circuit and an algorithm is a little bit pedantic, honestly. Sometimes algorithms will involve classical bits, right? So the example I gave earlier was with quantum teleportation. We had to talk about sending classical bits around. A circuit is usually talking just about the quantum stuff, right? Qubits and gates. And then finally, we have applications, right? So this is the highest level. This is the interface with the real world. And applications are basically quantum algorithms aimed at solving real world problems, right? And so the examples I gave before are here. Grover's algorithm, as one example, does database search and optimization. This has applications in finance, ecology, chemistry, probably a bunch of other things. Shor's algorithm and quantum key distribution, we mentioned these a couple of times, even though we didn't full on cover them. These have applications in cybersecurity and cryptography. And then finally, another one that's quite promising, even though, again, we didn't have time to get to it, but we totally could have. You have the tools you need, is simulation of quantum systems. And actually, this one, interestingly enough, was kind of the first, this was the initial motivation for quantum computing, was people noticed that it was super hard to simulate quantum mechanics on a classical computer. And then they thought, well, how should we simulate quantum mechanics? Can't we just use, quantum things themselves to simulate quantum mechanics? Turns out it's a bit more complicated than that. That's why, we're still researching and actively studying this. But that was one of the initial motivators, and it is indeed one of the most promising applications today. Okay, so let me pause here and I'll answer just a couple more questions. We are just about at the end of the lab time here. This is the end of the review. So I don't have any more review content to go over. I actually think I'm going to pop up the post-lab Zoom feedback at this point as well. I do just want to point out that there is some more content coming, but it's more sort of fun content for you to think about. I will go through all of these layers again and talk about some of the research, like active areas of research within each of those layers, just so you have some idea as well about what people are working on. Because each of these 5 layers that we have very briefly introduced you to in this course, each of those has many active areas of research inside of it. And I think this might just be helpful if you are considering doing more education in quantum computing. You should know what sorts of things people look at each of these different levels. So that's what I'll be going over at the end. This is the end of the review, though, of the actual review content. Okay, so let me just go back and check questions. So somebody says, I have a question. Since quantum computers still present their output as 0 and 1, is it correct to say that quantum computers' efficiency is less the more output heavy the algorithm being run is? Yeah, that's an interesting perspective. I don't think I've really heard it phrased that way before, but I think that's valid. Certainly, the fact that you can only measure zeros and ones at the end of a quantum circuit, that is one reason why designing quantum algorithms is hard. So just as one example, think back to the Deutsch-Jozsa algorithm. So that was the example where we had a function f that took a binary input, and it could be constant or balanced. And then we wanted to figure out if it was constant or balanced. In this case, the quantum computer only has to apply the oracle once, and that's why we had our speed up. But notice that we can still only measure one bit of information from that circuit, right? Even though the quantum computer, in effect, computes f of 0 and f of 1 at the same time, there's no way for us to measure both of those results. So I think the way that I have heard it phrased before is because you can only measure classical bits of information at the end of your circuit, that is sort of a limit on just how much speed up you can get from a quantum computer. You have to be really clever about what you measure at the end, because ultimately the amount of stuff you can measure is no different than the amount of stuff you could compute on a classical computer. You just have to make sure that the stuff you're measuring is more clever and more useful than what you would compute on a classical computer. Okay, so we are at time here, so I'll just kind of take a quick pause to say, again, required content is done. That is the end of the review. If you have to head out, no worries. But to end this off, I'm going to answer a couple more questions, and then I will be talking about active areas of research at each level of this sort of rainbow-looking diagram here. And then just one final reminder, there is a lab next week where we'll be talking about near-term quantum algorithms. But for this week, good luck with the technical assessment. Please fill out the survey. It is very helpful to us, and I promise we really do read these things. And yeah, so if you have to head out, feel free to head out. But otherwise, let me keep addressing some questions here. Okay, somebody else asks, we have used 2 qubits for implementing the quantum algorithm and circuit for the demo purpose, but what if we want to use more qubits, say like 50, for implementing an algorithm? What should be the logic? How should we think of designing the algorithm or circuit? Yeah, this is a great question. As you said, all of the stuff we covered in this course was usually only 2, maybe 3 qubits, right? We taught it that way because the 2 qubit variant is often easier to understand and easier to follow when you're first learning the algorithm. But all of the algorithms you've learned here, Deutsch-Jozsa, superdense, well, okay, let's say Deutsch-Jozsa and Grover search as 2 examples. Both of those can be extended to any number of qubits you want using very similar ideas to what we taught. So I think I actually talked about the multi-qubit variants in both of those lectures briefly. So if you're curious, you can go back and watch those. But suffice it to say that what we've taught you here is the building blocks to be able to extend those ideas to any number of qubits. For something like superdense coding or quantum teleportation, you can literally just copy paste the same circuit for however many bits you want to deal with, right? And so that's a pretty straightforward extension. Okay, somebody asks, where is the technical assessment test? I can't find one on Canvas. Interesting. I would have assumed it was on Canvas. If not, I guess it will be posted soon or sent out soon. I'm not 100% sure. Maybe I'll also make a note to ask about that. If it is late coming out, or if they haven't posted it yet, by the way, I would imagine that they'll give you an extension on that 3-day deadline, just if anybody was concerned. Okay, so somebody asks, can I talk more about oracles? Sure. I guess, well, I sort of don't want to do a full review of oracles right now, just because I think I have discussed that in previous labs. I'm happy to include a link to that in my announcement that I send out. I guess if anybody has specific questions about oracles, maybe I can answer those. What I will say as my own high-level review of oracles, though, just like when we learned about linear algebra, we learned this big word called a linear combination. And my advice to you was whenever you saw that word in a question, just mentally cross it out and replace it with sum. It's going to make it easier to understand, right? With oracle, we can do the same thing. Whenever you see the word oracle in a question, mentally cross it out and replace it with the word function. That's all it is. It's a function that takes some inputs and goes to some outputs. There's some more subtleties to that we discussed in the lab, but at the end of the day, an oracle is just a function. Okay, somebody asks, what's the time for the evening lab? I'm not sure. I imagine there's a lot of labs that happen in the evening, and it also depends on your time zone. Maybe if you can clarify, I might be able to help out. Can you share the previous polls? Yes, sorry. So this was the post-lab Zoom feedback. Oh, whoa. There we go. Okay, let's see. Making a career in quantum information, what should I be focusing on? It's a really open-ended question. I think one of the neat things about quantum information and quantum computing is that it's so multidisciplinary. So what I would say is if you start studying computer science, math, physics, or engineering, all of those four things can eventually lead you to quantum computing. At this particular point in time, there are no universities that I'm aware of that do undergraduates in quantum computing. Of course, you can do masters and PhD, but for undergrad and even high school level, those would be the subjects to focus on, right? Your computer science programming, your mathematics, your physics. That's really, all of those things come together to create quantum computing. Yeah, the technical assessment, somebody else is asking about that. I don't know, but I will follow up on that. General questions about quantum computing research career, sure. I might wait to answer that until after I finish the slides here. But yeah, absolutely. Okay, so somebody asks, in a unitary evolution of a qubit, the qubit state rotates on the Bloch sphere. So how is it different from changing the phase? It's not different, I would say. So you can certainly have a quantum gate, a unitary evolution, as you call it, which is, by the way, just the same as a gate. You can have a gate that just changes the phase. You can also have a gate that changes the superposition. You can also have a gate that changes both, right? So as you said, all of these gates are just rotations of the Bloch, like on the Bloch sphere. We had a whole lab where we talked about how you could have, rotations around the x-axis on the Bloch sphere and how that related to an x gate and so on and so on. That's a totally valid way to picture things, and that's often why we use the Bloch sphere, because then we can easily visualize how these qubits are being rotated around. Okay, so I think there are a lot of other questions here, including in DMs. I'm going to press pause on questions for now, just so I can finish off the slides, but then I will come back to questions after I finish the slides here. Okay, so let's move on to the next slide here. As I mentioned, the last part of this is just going over research questions that are being asked at each different level of this sort of quantum stack, right? So we went from inside out at first. Now I'm going to go from outside in, just to change things up, I guess. So if you are working at the applications level, this is, as I said, the closest to the real world, right? This is looking at how we apply algorithms to real world problems. Some examples of questions. I'm not going to read through all the questions. You can check this out afterward if you want to. The one I'll just point out, though, because it's coming up next week, is this one. What are quantum computers actually useful for right now? What can we do with noisy quantum computers? So last week, when we talked about RB, we saw that, even on some of IBM's commercial grade quantum computers with 3 qubit circuits, which is, not a ton of qubits, we had the solution was only correct 90% of the time, which really doesn't seem very good, right? And that is characteristic of a lot of quantum computers these days, that they have pretty terrible error rates, relatively speaking. It turns out, though, that people have done a lot of research into how you deal with noisy quantum computers, or you might also sometimes hear them called NISQ, which stands for noisy intermediate scale quantum, I think. But basically, yeah, these are our near-term, quantum computers that we have today or in the next 5 years. Yes, they're noisy, but what can we do with them? Can we still do, again, to this point of applications, can we still solve real-world problems even with a super noisy machine? Turns out the answer is yes, and that's what we'll be talking about next week. There are also some more sort of, I guess I'll call them like softer or non-technical questions that you can ask, right? A lot of times people think about quantum computing and research and physics and stuff as being highly technical, writing math equations all the time. Not necessarily. I know lots of people who work in these two areas. right? Looking at government policy, for example, of how society prepares for changes in the workforce or in how societal infrastructure works as a result of quantum technology. Another one that is super important is how we ensure equitable access to these new technologies. These are questions that cannot be solved with math, but they're still really important, and lots of people dedicate their careers to these questions. Moving down a level in this stack then is looking at algorithms, right? So people who study algorithms are normally concerned with questions like, how many qubits, what level of connectivity. So remember, this is referring to which qubits you can do 2-qubit gates between. Do we need to implement different quantum algorithms, right? And this is a really important question because today's quantum computers, the hardware is being developed very much in close collaboration with the algorithms, right? The algorithms people will tell the hardware team, I could really do a really awesome algorithm if you give me 12 qubits that are all connected to their neighbors. Then the hardware team will be like, awesome, cool, we can build that. And then you have to figure out what algorithms you can run with that particular connectivity, with those particular qubits, et cetera, et cetera. And again, I'm not reading through all the questions here, but feel free to go back and peruse on your own. For circuits, now, I guess another note I will make here is that as we're moving from the outside in, we're kind of getting closer and closer to physics, right? So by the time we get down here, this is going to be super physics oriented. Out here, it's going to be a little bit more about society problem, like real world problems, etc. Up here in algorithms, we have more of the computer science side. When we get to circuits, circuits is starting to look at, again, it's getting closer to the physics. It's starting to look at how we string gates together, right? And so the biggest concept in this is gate fidelity. How can we put gates together in such a way that they don't exacerbate errors too much, right? And then another one, which I will point out here just because it's my area of research, is how do we convert code into a circuit, right? So, I mean, it's obvious how you go from code to a circuit like the ones we saw drawn earlier, but how do you actually optimize that circuit for a particular quantum computer, right? Are there some operations that are easier or less error prone given a certain hardware implementation? Those are all questions that you would ask on this layer. Taking another step down into operations, here we start talking again more about physics, right? So if I give you a gate, like I say, please give me a Hadamard gate, this is the study of how you do that, right? So for example, an ion trap, this would be a lot of photonics, understanding how lasers work, laser physics, how all of these things can do something like a Hadamard gate. Let's see, what's another one here? I guess the other one that counts here for measurement is also, or sorry, for an operation is also measurement, right? You can study how to do gates. You can also study how you do measurements in a way that, actually preserves the measurement outcome as well as possible. So last week we talked about measurement errors. How do you cut down on that? How do you make sure that given a ket zero state, you come up with the measurement result 0 as much as possible? And then finally, the most physicsy, the most sciencey of all of these is definitely the study of qubits. And that is basically looking at a whole bunch of physical processes that could represent qubits and how you make them better qubits. So one sort of figure of merit for making a qubit better is improving the coherence time. We also talked about errors last week. So how can you reduce, or sorry, how can you increase, I guess, T1 and T2 times to decrease the error due to relaxation and decoherence, right? And in order to do that, you have to have a pretty good understanding of how the physics works underlying your qubits. So that is obviously just a very fast overview. Each one of the bullet points on each one of those slides is a whole area of research in and of itself. So my question to you, for you to sort of take away from this lab and to think about on your own, if you want to continue with quantum computing, is which of those sounds interesting to you, right? What would you like to work on? As I said, this can be a rough guide for the types of topics that you cover. So if you're interested more sort of on the top side here, you're probably going to be looking more in computer science and math. And if you're interested more in the bottom side here, that's probably going to be more physics, well, and also math. I guess math is everywhere in this, but that's generally how it works. But of course, this is not exact. This is only a guide. And at the end of the day, this is a huge industry that you could spend years learning about yourself. And so this is just supposed to be a very high level taste and guide of what might be interesting for you going forward. Okay, so wrapping things up then, key takeaways here. I think I already, this whole lab was basically key takeaways of the course. But yeah, you've come a long way. We've learned a lot of stuff. So definitely don't feel bad if this was a little bit overwhelming. You know, teaching quantum computing at this level, in this time scale, online, like all of these things are new for us. It's probably new for you too. And so this was a lot of content. It was a challenging course, and I think all of you should be proud of what you've learned. This point I think is really important to drive home, and that is that even though the name of this course is Intro to Quantum Computing, a lot of the concepts we've taught you, like probability, linear algebra, programming, complex numbers, these are useful for pretty much any field in STEM generally, right? So even if you end up not going into quantum computing, I hope that you will still find many of the lessons from this course extremely useful in your future career. And then finally was at the very end here. There's many different questions that need answers in quantum computing, and all of these pretty much are still open areas of research. And then, as always, we have our further reading here at the end of the slides. Okay, so I will end off the lab there. That's the end of the slides that I got. So I think, well, as with last week, I don't have any optional content, so I'll just be going back to answering some questions. Okay, so let's see what people are asking. Okay, so somebody asks, why would you describe the oracle as a genie at the very beginning? So remember, that was one sort of analogy we had, was that the oracle was like a genie where you ask it a question and it gives you an answer. Even though we still have to know, that to compute or to run the computation or do the algorithm. Yeah, it's a good question. And I think I think the best way to understand oracles would be to walk through the Sudoku example in the Qiskit textbook. So why don't I'll include a link to that as well. I'll have a whole bunch of links coming at you in my announcement. But this example gives you an example of a non-trivial oracle, right? So in the Waldo oracle, when we were searching for Waldo, it wasn't the best example, I guess, because it seemed like we had to know where Waldo was in order to build our oracle. I talked a little bit more about this in a previous lab, but suffice it to say that oracles are often more about enforcing constraints. And for a lot of problems in computer science, it's easy to enforce constraints, but hard to figure out a solution that abides by those constraints. And that's where something like an oracle in Grover Search comes in handy. So if you're curious about that and sort of how oracles might work in the real world, highly recommend the Sudoku example. I think it does a good job of explaining how you can specify constraints without actually solving the problem. Okay, so somebody asks, do you have any tricks to learn and remember linear algebra? I do learn and understand them, but forget it so easily. I'm sure there's a lot of acronyms out there for remembering how you do like, matrix vector multiplication and that kind of stuff. At the end of the day, though, I think it's really just practice. The more you use these things, the more it'll just become muscle memory, how you perform these operations. And especially if you go into a STEM field, you might be using terms like eigenvalues and eigenvectors in your everyday work. And so in that case, it would become something that you're practiced and experienced with. I don't really have any good tricks to memorize it. One thing I would say, which is not necessarily a trick to memorize, but a very good resource for understanding linear algebra and possibly thereby being able to remember it better, is a YouTube series by 3 Blue 1 Brown called The Essence of Linear Algebra. I will also include a link to that. It's probably like a couple of hours of YouTube videos, totally freely available, assuming you have access to YouTube, that gives you some great visualizations and more visual definitions of all the stuff we've learned in linear algebra. So for example, what does an eigenvalue look like? Right? That's something we didn't really have time to jump into, but these visual interpretations might help you remember better. Okay. Can you talk a bit about the role of mechanical engineering in quantum computing? Mechanical engineering, interesting. Off the top of my head, that seems like a less relevant, though maybe not totally irrelevant. It seems like a less relevant type of engineering. I think the type of engineering that most readily goes with quantum computing is electrical. And the reason you need electrical engineering is because a lot of these systems, for example, lasers in ion traps, yes, you need an optical physicist to figure out what the laser should be doing, but these lasers are often so high performance, so fast, so high energy that you need an electrical engineer to figure out how you control the laser and how you actually make the laser do what it should do. So these systems of how you do very precise timings, very high power being delivered to certain items in a circuit, that's an electrical engineer's job. And so I think electrical engineering is certainly quite relevant to building physical quantum computers. Maybe mechanical engineering is too. I'm not really as familiar with those applications though. Okay, so somebody says here, yes, linear combination equals sum. What does an oracle equal? Function. So yeah, sorry if I was just, my handwriting might not have been very neat there, but an oracle is supposed to be equal to a function, exactly. Technical assessment, I will follow up on. Okay, so somebody asked, can we solve the traveling salesman problem, or TSP, it's often abbreviated to? Since something like Grover's algorithm is better at optimization, my guess would be yes. My guess is also yes. I think, so TSP can certainly be phrased as an optimization problem. And I would imagine that you can translate that into a Grover oracle. I haven't seen that actually written out anywhere. And so I guess I don't know for sure that you can do it. Maybe there's some glitch that comes up that makes it not a good fit for Grover's algorithm, but I feel like it should be. It could be an interesting problem to think about, actually. How would you encode, because TSP requires a graph, right? Remember, the traveling salesman problem was if you have all these cities that are certain distances apart, and you want a mail person to deliver to all of these cities, visiting each of them once, how do you do that most efficiently? This would actually be pretty interesting to think about, because you have to think about how you would encode this, right? How would you even get a solution to TSP? What would that look like in terms of qubits? How would you design your oracle? So there's a lot of interesting questions there. I think at first glance, though, it seems like that should be a good application. All right. So somebody asks, can we ever build a quantum computer with 0% error rates like today's classical computers? Is that even physically possible? Okay, so two questions there. Can we ever build quantum computers with 0% error rate? No. Unless we have a truly foundational difference, or sorry, like a foundational change to how we understand physics, the answer is no. There are always going to be physical imperfections in our quantum computers. They are always going to have non-zero error rate. The next thing you say, though, is like today's classical computers. Today's classical computers do not have 0% error, believe it or not. They have very, very, very low error rates, right? So, I mean, I don't know the numbers off the top of my head, but in your average laptop, the probability that a single bit in memory randomly flips is like 10 to the minus 6, 10 to the minus 8, something like that, right? So versus on a quantum computer, you have like a 10% error rate. So classical computers are not perfect, and we will never have classical or quantum computers that are totally perfect. But we've gotten really, really good at mitigating errors in classical computers. And so even when one of those very rare bit flips occurs, your computer has software built into it that is constantly checking. It has some redundancy built in, so it can detect when an error has occurred, and it'll just go and fix it. And on the very off chance that a whole bunch of errors occur in a small period of time, your computer crashes. And sometimes that happens. Okay, can fault tolerance be introduced using AI or machine learning? Like the circuit keeps learning from faults and knows what can go wrong. Pretty far-fetched, I guess. Actually, not far-fetched at all. That is an actual use of machine learning in quantum computing, is to try and learn a model for the quantum computer's errors. Oftentimes, that is easier than doing explicit experiments to figure out each different type of error and to categorize all the different types of errors. A lot of times it's faster and easier to just let a machine learning model learn it for you. And so, yes, that is actually used fairly frequently. All right. Do we have semester 3 and semester 4? I don't think so. And I think generally speaking, the idea of having a follow-on to this course that goes into even more depth on quantum computing probably is not going to happen in this next year. But hopefully we can start providing more resources for where you can learn more if you're interested. Okay. Is it possible to use Grover's search in embedded programming? Interesting question. I'm not exactly sure I know what you mean here. Um, I guess if you're talking about doing certain optimization problems for the design of embedded circuits, probably, right? Again, I would imagine that most optimization problems can be translated to Grover search, or sorry, I know that most optimizations can be translated to Grover search. Whether these particular ones could be, you'd have to sit down and work it out, but I wouldn't be surprised if it could. Um, the Sudoku example I mentioned, we actually never went over it in lab. It's in the Qiskit textbook, but I will send a link to that in my announcement follow-up, so you'll have it there. Okay, yeah, some people in the chat are giving examples of mechanical engineering. Perfect, thank you for doing that. Yeah, I wasn't too sure. Okay, so somebody asked in a direct message, I'm considering a career in quantum computing research, and they are currently in first year undergrad taking physics. What next steps do you think I should take after this course? So my recommendation would be a couple of things. Number one, certainly continue in a physics program. That's great. It's going to be useful in quantum computing. Number two, I would say, if you're only in first year right now, maybe wait another year or so. But as soon as you can, try and get involved with some quantum computing research, right? If it goes on at your school, great. If it doesn't, try emailing profs at other schools. Cold emailing doesn't have a very high success rate, but it is certainly a strategy that you can try. In my opinion, now that you have learned everything in this course, you have enough of the high level ideas that you could legitimately walk into a quantum computing lab, have a few weeks of orientation, and actually be doing research, right? So absolutely take more quantum computing classes if they are offered. It never hurts to learn more. But these are the fundamentals that you would need to at least be able to talk with a researcher and understand what they're saying, right? When they talk about qubits and when they talk about matrices and when they talk about eigenvalues and Grover search and oracles and all that kind of stuff, you know those things now. And so yes, further education would be nice. If you could take like a university level quantum computing course, it would cover all of these things, but go into more depth on all of them. But realistically speaking, now is as good a time as any to just start doing some research. And that would be my biggest piece of advice. Okay. Can you state one major limitation of using real numbers in quantum mechanics? Complex numbers are used to represent interference and phase difference. Can't that be done by real numbers? Is the two-part representation of complex numbers the reason it's used? I think my biggest reasoning for why you need to use complex numbers is phase, right? And why you need to use sort of two numbers. If you only used real numbers, right? If you only used real numbers in your vectors, I can't think of a way that you would represent phase with this. Now, a caveat, I guess, of course, you can represent qubits using only real numbers. You need more than two of them, right? But, well, actually, wait. I guess on a block sphere, you can, well, okay, yeah, there's a couple of caveats here. So one representation is a block sphere, right? And on a block sphere, you can obviously represent a qubit using only two numbers, right? You only need your theta and your phi, and both of those are real numbers. So you could represent everything using vectors of theta and phi, and that's valid. But then you have to ask the question, is it easy to do matrix operations? Like, how do you apply gates to that? Okay, well, maybe it's rotations, but then how do you apply a rotation to theta and phi? Maybe that's not always obvious. The other thing that you do have to consider is when you go up to more than one qubit. And that's where phase really starts to make a difference, because one thing that the block sphere does not capture is phase, right? The states ket 0 and minus ket 0 are represented by the same point on the block sphere. Those are both the North Pole. But if you had states like, kets, what's a good example? If you had a superposition state where you had, is this a good example? Well, sure, we'll go with it. If you had superposition states like this, oops, sorry, ket 0, then this portion here is obviously not the same. And again, that's where the difference in phase comes in. So these are kind of hand wavy, and I don't really have a nice cohesive answer for you here. But I think the general intuition, right, for the reason we need two-level systems is because you have both superposition and phase, right? And each of those requires one real number to keep track of them. And when you go up to more than one qubit, oh, my fire alarm is going off. Hold on. Okay, so they've just said that they'll be testing the fire alarm system with no heads up, unfortunately. Okay, hopefully that's not too loud. It's kind of loud. So I apologize for this. Yeah, I don't know. Okay. Hang on. Okay, so yes, to everybody saying, am I fine? They've said it's just a test, but it is gonna go off. Hopefully it's not too loud. We'll see. Anyway, my apologies for that. They didn't give us any heads up, so I was not able to prepare. Anyway, where were we? Yes, explaining superposition and phase. I don't think I really have any better explanation here. The reasoning for why you need two-level systems and you need complex numbers actually has a pretty deep meaning in group theory, which is a branch of mathematics that I am not super familiar with, full disclosure. So I'm not sure I can really provide any better intuition than just you have to capture both of these aspects for possibly many different qubits. Okay, let's try and get back to things. Okay, so somebody says, yeah, if you finish your undergrad in computer science, you want to continue in quantum computing. Do you continue and do a master's in CS? Because you probably don't see a master's in quantum computing. Right. So actually, I was just looking at this. I was thinking about doing a master's. As far as I'm aware, the University of Waterloo, which is the school I went to, is at least one of the only ones in the world that offers a master's in quantum computing. So it's certainly not very common. As far as what you want to do in a master's, though, a master's in physics, math, or CS would probably all be great, right? And I imagine in all of those, it's going to be more important that you find researchers and find collaborators who are working on quantum computing rather than necessarily taking coursework that's directly focused on quantum computing, because oftentimes that just doesn't exist. It's such a new field that it could be, excuse me, it could be hard to find actual quantum computing courses. So my advice there, again, would just be try and get involved in relevant research as soon as you can. And then you can use all the stuff you learn in math, physics, and CS courses that can then, that stuff can then be applied to your research. Okay, yeah, so all these questions about sort of following up on undergrads and that kind of stuff, that would be my advice. Can we use Grover's algorithm for searching for a value in a large database? It will still be better than ON. Yes, so Grover's algorithm will be order root n. So actually, the improvement over just a classical search gets even more and more as you get a larger system, right? So regular linear search, as we learned, is order n. So if I were to graph that, the size of your DB would be down here. And the complexity or the time or the effort or whatever would be up here. The size of the classical search grows linearly, right? So this would be your linear search. Whereas Grover is going to be root n, right? So as your database gets bigger, you're actually going to observe more and more significant improvements using Grover's search over using linear search. Okay. So why are we using exclusively complex numbers, but a different two-tuple with real scalars? With scalar multiplication and vector addition defined, say something more suitably to quantum mechanics, as we already used complex numbers as of now. So I think this is, again, along those same lines where I don't really have a better answer than what I have already said. I totally acknowledge that you can use two real numbers to represent a single qubit. It turns out you need a third, fourth, fifth, sixth real number to represent each qubit on top of that. In addition, I don't know exactly how many degrees of freedom that works out to be, but I do know for sure that using two-dimensional vectors of complex numbers works, right? And that's why we use it. Okay. Yeah, so I know that this question has been asked a couple of times. I don't really have a better answer, unfortunately. Like I said, I think understanding this difference between superposition and phase is the biggest part of it. I don't really have a better answer, unfortunately. All right. Oh, okay. Apparently ETH Zurich has a master's in quantum engineering as well. There you go. All right. So how do you keep interest in quantum computing than more application-based things like machine learning, since I'm in CS? Okay, yeah, for me personally. I mean, I honestly think that so machine learning, quantum computing, many other fields in computer science, they have pretty different feels to them, right? And so I did a little bit of research in machine learning a few years ago. And at least my experience was that it was a lot more kind of data science-y. And all I mean by that is, it's statistics-based. It's a lot more about running experiments, running computer programs that learn over time, right? That's kind of the definition of machine learning. Quantum computing, at least as of right now, feels a lot more like it relies on pure math, right? So in my research in quantum computing, I spend a lot more time day to day literally writing out math equations and solving them than you ever would in machine learning. And I think that is just by nature of the progression of the field, right? In machine learning, a lot of that pure math foundation has already been laid, whereas in quantum computing, a lot of that still needs to be done. So I think for me, I just enjoy working on a field that is so much newer. There's so much more that's ready to be explored. For me, it feels like there's a lot more flexibility in what you can do, because machine learning is very popular, right? A lot of people do it. And if you wanted to do research in it, you would be more constrained to a particular area than you ever would be in quantum computing. So that's one answer. I think generally speaking, I just find the math involved with quantum cooler. I enjoy working on it more. Um, so there you go. Let's see. Yeah, so I guess the remaining questions here are mostly about following on this course, doing more education in quantum computing, whether that's a master's, PhD, undergrad, whatever. And like I said, I think for all of those, I would say keep taking technical subjects, right? Learn about quantum physics, learn about mathematics, take linear algebra courses, take computer science courses. All those things are going to be useful. But I think at some point, especially after you've done this course, the next step is just going to be to start doing research in some type of quantum computing. I would also remark that when you're sort of first taking your step into this industry, don't be too picky, right? Like I know we asked this question about which of these areas sounds most interesting. That is totally good to think about and have as a goal. But if you're interested in algorithms and you get offered a research position in circuits, take it, right? Any experience working with quantum computers and working in that area of research is going to be valuable. And so that would be my advice there. Topological insulators. I don't know what those are, unfortunately. For quantum gates. Oh, like topological qubits? I know that's a thing. I'm not sure. Even topological qubits, I'm not too familiar with. But that's something that Microsoft has been betting heavily on. So I'm sure that if you went and read Microsoft's it was like Q# documentation, you'd probably learn a little bit more about topological qubits. All right, so I think I will probably wrap things up there. I think I've gotten to the end of the questions. But if you do have any other questions, as always, please feel free to post on Piazza. As one final reminder, there is the sort of summative technical assessment this week. Next week is going to be kind of a hype, looking forward, whatever, near-term quantum algorithms exploration. And so I look forward to seeing you then. Other than that, good luck with the assessment. Have a great week, and I'll see you again in 7 days. Bye, everyone.